Hello, my name is Julia Stoyanovich. I am an assistant professor of computer science and engineering and of data science, and director of the Center for Responsible AI at New York University. Today, I will be discussing the challenges of designing, developing, and deploying data-intensive systems responsibly. I am speaking specifically to the technologists, such as myself, who tackle these challenges as part of their day-to-day work. I will be treating these challenges through the powerful lens of equity. Equity as a social concept, treating people differently depending on their endowments and needs to provide equality of outcome rather than equality of treatment, lends a unifying vision for ongoing work to operationalize ethical considerations across technology, law, and society. I would like to present a vision for building data equity systems that consider equity as an essential objective. To motivate the work on data equity systems, let us consider automated hiring systems. Since the 1990s, and increasingly so in the last decade, commercial tools are being used by companies large and small to assist in the hiring process. This process has been aptly described as a funnel, a sequence of data-driven, algorithm-assisted steps in which a series of decisions culminates in job offers to some candidates and rejections to others. As stated by Jenny Yang, former commissioner of the US Equal Employment Opportunity Commission, automated hiring systems act as modern gatekeepers to economic opportunity. Why are algorithmic hiring tools so attractive? First, they help employers, large and small, to hire more efficiently, source and screen candidates faster and with less paperwork, and select candidates who will likely do well on the job. These tools are also meant to improve efficiency for the job seekers, allowing them to apply with the click of a button, matching them with relevant positions, and facilitating the interview process. We also often hear the argument that the use of these tools can help us improve workforce diversity. Indeed, an argument being made very frequently is that because humans are biased, we have no choice but to use machines to step in and hire on our behalf. I'm showing you here an excerpt from a famous study by Bertrand and Mlinspect, who back in the analog days of 2004 manipulated perceived gender and race on resumes and observed that applicants who were perceived as male and white received substantially more callbacks on the very same resumes. Are algorithmic hiring tools living up to their promise? One of the earliest indications that there's cause for concern came in 2015 with the results of the Ad Fisher study out of Carnegie Mellon. The authors ran an experiment and found that ads for high-paying jobs were shown far more frequently to men than to women. This brings back memories of the time when it was legal to advertise jobs by gender in newspapers. In late 2018, it was reported that Amazon's AI recruiting tool, developed with the stated goal of increasing workforce diversity, in fact did the opposite thing. The system taught itself that male candidates were preferable to female candidates. It penalized resumes that included the word women's, as in women's chess club captain, and downgraded graduates of 2 all-women's colleges. Other examples of discrimination include shutting out people suffering from mental illness, such as depression or bipolar disorder, on the basis of online personality tests, even if they have the right skills for the job, and of showing ads suggestive of a criminal record when Googling for African-American sounding names, far more frequently than when Googling for white-sounding names, even when controlling for whether the individual in fact has a criminal record. This is problematic because employers often Google for an applicant's name as part of a background check. To summarize, we are concerned about the use of data-driven algorithmic systems in hiring. Their effects are often discriminatory, reinforcing results of historical disadvantage. Discrimination is often linked to the term bias, a term that is used by the technical community ever more frequently, but that is still poorly understood. We will discuss bias in a couple of minutes. In addition, or perhaps even before worrying about bias, we should ask whether these tools actually work. Are they picking up useful signal from the data, or are they an elaborate coin flip at best? As Arvind Narayanan, computer science professor at Princeton depicted here, puts it, are these tools AI snake oil? If a tool helps improve workforce diversity, it admits a sufficient number of candidates of each required demographic or socioeconomic group, but its decisions are otherwise arbitrary. Can such a tool be considered fair? What if these decisions are worse than arbitrary? What if they are picking up signal like a person's disability status, and we have no way to know that this is happening? What if it's measuring something about a job applicant that we have no reason to believe to be relevant for the job for which they are applying? How can we know whether a tool works? Well, AI tools are engineering artifacts. We should not take the claim that they work on faith. To know whether they work, we should use the scientific method. Formulate a hypothesis that states in a falsifiable way that the tool indeed selects employees who do well on the job and is better at predicting that than a random guess would be. What is falsifiability? The philosopher of science Karl Popper explains it eloquently, stating, a theory or idea shouldn't be scientific unless it could, in principle, be proven false. In the complex ecosystem in which automated hiring tools are commissioned, developed, and used, we must ask ourselves, who is responsible for ensuring that these tools are built and used appropriately? Who is responsible for catching and mitigating discrimination and due process violations, and for controlling the proliferation of snake oil under the fancy label of data science and AI? We all are responsible. But what can we as technologists do? What specifically is our role and our responsibility? To answer some of these questions, let us step back and think carefully about the role that technological interventions, such as data and model debiasing that you may have heard about, can play in supporting the responsible use of data-intensive systems. This discussion is necessary to help us find a pragmatic middle ground between two harmful extremes. The first is techno-optimism, a belief that technology can single-handedly fix deep-seated societal problems like structural discrimination in hiring. And the second is techno-bashing, a belief that any attempt to operationalize ethics and legal compliance in data-driven systems will amount to fairwashing and so should be dismissed outright. The goal of my talk is to help us find this middle ground. Let's dive right in and discuss bias and make a connection between bias and data equity systems. In their seminal 1996 paper, Batya Friedman and Helen Nissenbaum identified 3 types of bias that can arise in computer systems, represented here as a 3-headed dragon: pre-existing, technical, and emergent. Pre-existing bias exists independently of an algorithm and has its origins in society. Technical bias is introduced by the operation of the technical system, and it may exacerbate pre-existing bias. Finally, emergent bias arises in the context of use and may be present if a system was designed with different users in mind or when social concepts shift over time. We will fight the dragon, the bias dragon, with the help of data equity. Data equity has 3 major facets. Representation equity refers to deviations between the data record and the world the data is meant to represent, often with respect to historically disadvantaged groups. Access equity is concerned with having access to information, features, data, and models needed to evaluate and mitigate inequity. Finally, outcome equity refers to downstream unanticipated consequences outside the direct control of the system. I will now go through each of these data equity types to give the flavor of the positioning. As will become clear, technical solutions are useful, but purely technical solutions are never sufficient. They have to be based on explicitly stated values and beliefs that in turn arise through public conversation and societal consensus. Let's start with representation equity. Data is an image of the world. It's mirror reflection. When we think about societal bias in the data, we interrogate this reflection. One interpretation of bias in the data is that the reflection is distorted. We may systematically oversample or undersample particular parts of the world or otherwise distort the readings. Another interpretation of bias in the data is that even if we were able to reflect the world perfectly in the data, it would still be a reflection of the world such as it is, and not necessarily of how it could or should be. It is important to keep in mind that a reflection cannot know whether it's distorted. That is, data alone cannot tell us whether it is a distorted reflection of a perfect world, a perfect reflection of a distorted world, or if these distortions compound. Further, it's not up to data or algorithms, but rather up to people, individuals, groups, and society at large to come to consensus about whether the world is how it should be, or if it needs to be improved, and if so, how we should go about improving it. My final point here is that changing the reflection does not necessarily change the world. If the reflection itself is used to make important decisions, for example, whom to hire or what salary to offer to an individual being hired, then compensating for the distortions is worthwhile. But the mirror metaphor only takes us so far. We have to work much harder, usually going far beyond technological solutions, to propagate the changes back into the world, not merely brush up the reflection. Let me now give an example of a concrete approach that focuses on representation equity in set selection and ranking. These tasks are commonly used in a variety of domains, including also algorithmic hiring, a domain to which we referred in the introduction. Consider the task of selecting 4 candidates among 16 job applicants to invite to job interviews. Our goals are twofold. The first is diversity. We wish to include 2 candidates of each gender and at least 1 of each race. Our second goal is utility, maximizing the sum of scores of the selected candidates subject to diversity constraints. You can see a list of candidates in the table here, along with their scores. For example, candidate A has score 99 and L has score 83. We observe that male candidates have higher scores than do female candidates of the same race, and that whites have higher scores than blacks and than Asians. The highest scoring set of 4 candidates that satisfy the diversity constraints is highlighted here, with combined score of 373. If we consider the selected set more closely, however, we observe a problem. And that is that we picked the best, according to score, white and male candidates A and B, but did not pick the best black, Asian, or female candidates. Note that our example was deliberately constructed to highlight the following. If some population groups have systematically lower scores, then it costs less to skip their best scoring members in the name of diversity. This runs contrary to the nature of the diversity objective, which is to equalize access to opportunity. This also represents unfairness under a particular belief system. Suppose that scores represent effort. For example, how hard someone had to study to do well on a test. We may take a relative view of effort and assert that scores are more informative within a group than across groups. Further, we may assert that it is important to reward effort. Taken together, these beliefs correspond to a lack egalitarian conception of equality of opportunity, denoted here with the rainbow unicorn. But there is something we can do. Consider the set of 4 candidates highlighted in blue. This set still meets the diversity constraints, and its score is lower by 1 than the score of the pink set. This utility loss is inevitable, but it's very small. The blue set contains the top scoring candidates of both genders and the top white and black candidates. And so it's much better in terms of rewarding effort across groups. Having stated our beliefs and observed the trade-off between diversity, utility, and fairness, we are now ready to design an intervention. For example, we may compute unfairness for a group, like the female candidates, as the ratio of the score of the lowest scoring selected candidate, K with score 83, and the score of the highest scoring skipped candidate, D with score 95. We can then reformulate the selection process to balance unfairness across groups. We did this and quite a bit more in the paper, designing several fairness metrics of this sort for both set selection that I just described and for ranking. We devised an integer linear program to encode all of these constraints, and we ran experiments showing that the utility cost of balancing fairness is low in most cases. Let us now switch gears and discuss access equity. Access equity is concerned with having access to information, features, data, and models needed to evaluate and mitigate inequity. For the next couple of minutes, I will focus specifically on technical bias, on making sure that we're able to catch and correct the imperfections and distortions in the data as it travels through complex data science pipelines. Much exciting work remains to be done in supporting access equity, both in terms of practical implementations and in forming a conceptual understanding of the interactions between pre-existing and technical bias and their impacts on equity. The FAIR machine learning research community considers this work out of scope. Their focus is on predictive analytics that take as input a nice, clean rectangular dataset, crunch it, and produce a result. If we then notice that the result is such that no women are shown ads for high-paying jobs, and no Black candidates are invited for job interviews, then we have three choices. We can tweak the input data, for example, upsample or downsample some groups. We can tweak the algorithmic box, for example, add a regularization term, or we can tweak the result, for example, reassign outcomes. This is a useful exercise, but it's a limited view. I'm showing it here as fighting a paper dragon. To fight the three-headed bias dragon, we need to expand our scope and start asking what specifically happens inside the box, how are the results used, and where did the data come from? In other words, we need to take the life cycle view of equity. Let me give an illustration from the life of a data scientist. Consider Anne, a data scientist in a human resources department at a large retailer. Anne was tasked with developing a model that predicts the level of compensation to offer to successful job applicants to make sure that they are successfully hired. Anne includes candidates' self-reported demographic data together with their employment histories as input. Following her company's best practices, she starts by splitting her dataset into training, validation, and test sets. She then implements data preprocessing, joins the tables, and then interpolates missing values. And then after, she performs model selection, and finally, tuning and validation. Next, Anne considers the accuracy of the trained model and observes a disparity. Accuracy is lower for female applicants. This presents another kind of a fairness issue. Considering the complexity of the data processing pipeline, Anne has a long night of debugging ahead of her. Anne does go back to data preprocessing and observes that the value of the attribute age is missing far more frequently for female applicants than for male applicants. And she interrogates data interpolation, the method used to guess these missing values. She compares age distributions by gender and notices differences starting from the mid-30s, and revisits the data cleaning step and selects a state-of-the-art data imputation method to fill in age in customer demographics. This example illustrates a more general issue, that incorrect or incomplete choices during data modeling or data preparation can introduce systematic distortions in the data, affecting downstream performance. Other examples include systematically guessing a person's age or gender incorrectly, because these values are missing more frequently for some demographic groups than for others. Importantly, it has been documented that data quality issues, such as missing or dirty data, disproportionately affect members of historically disadvantaged groups. And we risk compounding technical bias due to data representation with pre-existing bias for such groups. In a recent line of work done jointly with Stefan Grafberger and Sebastian Schelter, we developed mlinspect, a lightweight data distribution debugger for data pre-processing pipelines. The tool is available in the open source. Check it out. The mlinspect tool extracts logical query plans, modeled as directed acyclic graphs or DAGs, as shown here, of pre-processing operators from machine learning pipelines that use popular libraries like pandas and scikit-learn, and combine relational operators and estimator transformer pipelines. These plans are then used to automatically instrument the code and trace the impact of operators on properties like the distribution of sensitive groups in the data. Recall the plight of Anne, our friendly data scientist, who is committed to respecting software engineering and data science best practices, but is challenged by the complexity of the pipeline and by the multitude of objectives, including accuracy and equity. How would Anne know whether the pipeline she has constructed works? The answer is seemingly simple. We must enable Anne to do sound scientific experimentation. Sebastian Schelter and I, and several of our students, built FairPrep, a system that supports data scientists by enabling sound experimentation. FairPrep is designed to enforce isolation of test data and to allow for customization through user-provided implementations of different components. In the remaining time, I would like to address the final and perhaps the most difficult dimension of data equity, outcome equity. It is concerned with whether and how we can assess and mitigate inequities that are outside the system's direct control. My thinking about outcome equity centers around interpretability and public disclosure. I like to think about interpretability using the nutritional label metaphor. The data management community has been studying systems and standards for metadata provenance and transparency for decades. The needs of data equity systems are once again bringing these favorite topics into the spotlight, but with a twist. To differentiate a nutritional label from more general forms of metadata, we articulate several properties. The label should be comprehensible. It is not a complete and therefore overwhelming history of every processing step applied to produce the result. The information on a nutritional label must be short, simple, and clear. It should be consultative, providing actionable information, not just descriptive metadata. Based on this information, consumers may cancel unused credit cards to improve their credit score, and job applicants may take a certification exam to improve their chances of being hired. Labels should enable comparisons between related products, implying a standard. Finally, they should be composable and computable, derived automatically as data and decisions are produced by the system. Bridging to the social aspects of interpretability, I am also working with colleagues in social psychology on a framework that forms connections between interpretability and trust and develops actionable explanations for a diversity of stakeholders, recognizing their unique perspectives and needs. An important point is that individuals and groups who distrust algorithms may be less likely to harness the potential benefits of new technology. And in this sense, interpretability intimately relates to equity. Recent studies found that individuals who are more familiar with AI fear it less, and are more optimistic about its potential societal impacts. Much more interdisciplinary work is needed, in which technologists engage with psychologists and social scientists and with members of the public to collaboratively design interpretability methods in support of outcome equity. I also believe that we technologists should be engaging and investing in education efforts to support outcome equity. An important component of this is courses that we develop and offer. I have been developing and teaching courses on responsible data science at New York University. The course I'm showcasing here is in its third year, and it has been able to attract an amazingly diverse and engaged group of students. All course materials are publicly available online at the link on this slide. I will also note that Fala Arif Khan and I have been developing a Data Responsibly comic series. Its first volume has been translated into Spanish and French, and translations of the second volume are on their way. It is now time to wrap up, and I would like to leave you with a few parting thoughts. It is clear to me that we, technologists, have an important role to play in the responsible design, development, and use of data science tools. However, an important thread that runs through our discussion is that we cannot fully automate responsibility. While some of the duties of carrying out the task of, say, legal compliance can in principle be assigned to an algorithm, the accountability for the decisions made by an algorithmic system always rests with the person. This person may be a decision maker or a regulator, a business leader or a software developer, or importantly, a member of the public. For this reason, I see the role of technologists, such as myself, in helping build systems that expose the knobs of responsibility to people. Of course, the systems we're helping build are not simply technical, they are socio-legal technical. In some sense, technology is the easy part. This means that to expose the knobs of responsibility to people, we must work together to create meaningful regulatory mechanisms. A topic for another talk. I also see as part of our responsibility as technologists and educators to help create a new generation of AI and data science practitioners and an informed public. To make progress, we need to step outside our engineering comfort zone and start reasoning in terms of values and beliefs, in addition to checking results against known ground truths and optimizing for efficiency objectives. This seems high risk, but one of the upsides is being able to explain to our children what we do and why it matters. Thank you very much for your attention.